Swayam Prabha. Digital India. Educated India.
Hello, welcome to Module 35, Wallman compactification continued. This time we will study universal property of Wallman compactification. So here is a theorem. The statement is quite elaborate here. Start with a compact Hausdorff space and a continuous function from x to y. Then, given an ultra-closed filter f1x, the image filter f check of f is convergent to a unique point f hat of f in y. It is convergent in y, and the convergence point is unique. That unique point, I am denoting it by f hat of f. That is the meaning of convergent to unique point here. Okay. After all, it depends upon both the filter as well as the function f. The association f going to this f hat of f, which you have just defined because of the uniqueness of the convergence of this f check of f. This is a continuous function from the space of all ultra closed filters, right? This is Wallman compactification to the given compact Hausdorff space, and it has the property that f hat composite phi is identically f, the original function f. So think of phi as an inclusion map of x inside Wx. This f hat is nothing but the extension of f. That is the way I would like to think of f. The third condition tells you the uniqueness of f hat itself, namely any continuous function g from Wx to y such that g composite phi is f is equal to f hat. Okay. So this is the universal property of the compactification that we are discussing now. So let us go through the proof of this one. Okay. So this is the picture that I have in mind of what I am going to do. Starting with a continuous function, of course we have to assume y is compact Hausdorff. Okay, I want to get a function here f hat. And I have already described how this function is got. Take an element here, that means an ultra closed filter. The image filter under f, that is a filter on y. It may not be ultra closed or anything, but it is what? It is convergent because y is compact. And that convergence is unique because y is Hausdorff also. So that is the function f hat. We have to show that this f hat is continuous and this diagram is commutative. Okay. Such a f hat is unique is the last part, the uniqueness here indicated by a sheik. Now suppose f check of f is not convergent in y. Okay. What does this mean? It means that for every y inside y, there exists a open neighborhood Vy of y in y which does not belong to f check of y, f check of f. So this is what we have seen earlier. Any filter does not converge means you have neighborhoods like this. Okay, does not converge. For every point you must have a neighborhood which is not in there. This is what we have used earlier also. But this is the meaning. What is the meaning of this? F of f inverse of ui. Ui is a neighborhood of y inside capital Y. So f inverse of ui, that is an open subset of x now. F of that is contained inside ui, right? So ui is also not inside f of f, right? If this ui is neighborhood ui which does not belong to f check of f, okay, means even this is not inside, because if this set is there, then ui would have been there because it's a superset, right? But this means that f inverse of ui is not in f, right? If f inverse of ui is not in f, then image of f would have been in f check of f. If it is in f check of f, then ui would be in f check of f. So that is the chain here. So what we have got is that an open subset f inverse of ui of x is not in f. Okay. Since y is compact, we can choose finitely many yi's such that y is covered by this finitely many open subsets u, y, i's. For each y you are getting this one now. But then what happens if you take inverse images of this, they will cover x. So x will be the union of iron 1 to f inverse of ui's. And this x is inside f. Again we are using the last thing that we have proved last time and we used it, now we are using it again here. So what does this mean? This means that one of them is inside f, and that's a contradiction. So we conclude that f check of f is convergent. So the point is, we are not proving f check is an ultra closed filter. If that is the case, then we don't need to repeat this proof. Okay, and it is not true also. It is not true that even it's a closed filter in general. Nothing is needed. Okay, we go back to x and do the work there and conclude that the image filter must be convergent, and the convergence is uniqueness follows because y is Hall star. That is an extra assumption. Okay. This proves one. So the function is there now. Automatically, what is this function? If you start with x here and go to phi x, what is phi x? Phi x is the atomic filter f. What is f check of phi x? It is f of fx. It is the atomic filter generated by the singleton fx, and that filter will not converge to any other point than fx, right? Therefore f hat of x must be equal to fx. F hat of Vx must be equal to fx. So if you come this way and go by f hat, what you get is f is the conclusion here. So that is what I have done here. Now I repeat it. Note that if f is fx for some x, which is the meaning of that this f is phi of x, that is the definition, right? Since fx converges to x, it follows that f check of fx converges to fx. This just means that f hat of Vx is fx. Okay, I saw it in a different way because f check of fx is nothing but f of fx, the atomic filter generated by fx. Okay, we need to show that f hat from wx to y is continuous, with the topology here being the Wallman compactification topology, whatever you have defined. So start with a u, a neighborhood of y in f check of f. F hat of f. F hat of f is some point inside y, okay, for some f inside wx. So I must produce a neighborhood such that that neighborhood goes inside u. Okay, choose an open set V such that y belongs to V contained inside V bar, contained inside u. I start with an open subset u, and which is a neighborhood of y, which is y I am assuming is f hat of f. Okay, so how can you get this one? This is because y is compact. Hausdorff means it is also regular. Compact Hausdorff space is a T4 space. Okay, so in particular it is regular also, and hence what we get is a neighborhood V, y belonging to V, contained in V bar, contained inside U. Now we claim that this f is inside f inverse of V plus. F inverse of V is open inside y. F inverse of V plus will be an open neighborhood, open subset in the Wallman compactification. I want to say that this curly f that we started with, this filter, is here. Moreover, under f hat, this f inverse of V plus goes inside U. So once I state it, it is very clear that this happens, but let us verify this one. Since y is f hat of f, that means what? It is the limit of f check of f, and that limit is inside V. We have this neighborhood V is inside f check of V. Okay, nx, the whole of ny is inside f check of f. So in particular V is here. Hence there exists some a belonging to f such that this fa must be contained inside V. V is a superset of fa. That is the way f check is defined. You take all image of members of f by little f and then take supersets. That is the way f check is defined. So there is some member here a inside curly f. F of a is contained in V. So that is the meaning of that V belongs to f check of f. But this means a is contained in f inverse of V, right? And this a is inside f. That means f inverse of V must be inside f, because f is a filter. That means this filter is in f inverse of V plus. Okay, one part is over. Now I have to show that this f inverse of V plus is mapped inside U by f hat. What does that mean? Take any ultra closed filter belonging to this set f inverse of V plus. Okay, look at its unique point to which it converges. That convergent point must be inside U. That is the meaning of f hat, right? So start with f prime inside f inverse of V plus, which is just the meaning f inverse of V belongs to f prime. Okay, what does this mean? F of this one will be inside f of f prime. F of f prime is contained inside f check of f prime. Okay, this is a set here, but that is contained in each member here. So this is a set of subsets, right? Each member here is contained inside this one. It belongs to this f check of f check. That is another family. Okay, so in particular, this f of f inverse of V is a member of f check of f prime. Since f of f inverse of V is contained in V, contained inside V bar, it's a closed set. So V bar must be inside this one. Okay, from the remark 7.43, which we have used several times, it follows that the limit f hat of f prime, the limit of this one, okay, f check of f prime, that must be inside V bar. Okay, and that V bar is inside U. In fact, it will be inside V also, right? For every V, if this one is there, the limit point must be inside that one. So V bar inside U. This completes the proof of the continuity of f hat, and hence that of the proof that of statement 2. Statement 2 is we wanted to show that the association defines a continuous function, and the commutativity is already seen very easily. Okay, now let us prove 3. But 3 is a consequence of the fact that phi x is dense in Wx and y is Hausdorff. Remember that if you have a Hausdorff space, suppose you have two continuous functions from one space to a Hausdorff space y, then the set of points wherein the two functions agree, that's a closed subset. Okay. Now apply that to this situation. You have two functions x2, y. Okay, what are they? You have actually two functions wx to y. What are they? They are both extensions of the same f, or you may say that phi composite f hat composite phi is f, is also equal to some g composite f. What does that mean here? If you think of phi x as a subset of wx, both of them may agree on phi x, but phi x is dense, therefore phi x bar is the whole space. If they agree on phi x, they must be agreeing on phi x bar, because phi x bar is the closure of phi x. So a closed set containing phi x must be containing phi x bar. That phi x bar is the whole space, therefore the two functions agree on the whole space. Okay, so this theorem is what we mean by universal property of Wx. It would have been fantastic if we could prove such a thing without y being Hausdorff, just y T1 space. Okay, unfortunately we are not able to do that. Okay, that is one of the drawbacks of Wallman compactification, I would say. All right. Returning to our remark 7.72, let us suppose that the Wallman compactification Wx of the space is Hausdorff. So I just made this remark. Okay. Take a special case, namely Wx is Hausdorff. Since a compact Hausdorff space is a Tikhonov space and Tikhonov property is hereditary, it follows that X is a Tikhonov space. Okay. So I said it would have been wonderful and all that, but the very fact that the Wallman compactification is meant to get a compactification of a larger class of spaces. Okay. So if you want it to be Hausdorff, you are forced to do it only for Tikhonov spaces. So this is an inherent, if you want to think of this as a weakness, then it is inherent in what you are trying to do. There is no other way. You cannot expect Wx to be compact, Wx to be Hausdorff all the time. Okay, that is not possible. That was not the intention of Wallman at all. All right. So that is the point of making this remark. So we have to accept it. All right. Having done that, let us see what we can do when it is Hausdorff. So X is already now Tikhonov space because Wx is Hausdorff. The moment it is a Tikhonov space, we can also get the Stone-Check compactification E comma Ex bar. So this makes sense. Okay. So what is the difference between these two compactifications is the natural question that we want to investigate now. Okay. So this is answered by the two universal properties of both these compactifications. So take Ex bar denote the Stone-Check compactification. By the universal property of Ex bar, okay, we have a unique continuous function phi hat from Ex bar to Wx such that phi hat composite is equal to phi. This is similar to what we have done for Wallman compactification just now. Okay. Moreover, since Ex bar is a compact Hausdorff space, we can apply the previous theorem, okay, just now that we have proved. We get a function E hat from Wx to Ex bar such that E hat composite phi is equal to E. Okay. So we did it for x to y, a function f, and then we call it f hat. Now this is f is E hat, E, so I have got E hat here. So what we have got is, here X is your space, which is a Tikhonov space. It is sitting inside Stone-Check compactification here and Wallman compactification there. Okay. So this is the Stone-Check embedding here, and this phi is the Wallman embedding. Okay, X going to the atomic filter effects. So what happens? This function gets extended to E hat. See, from here, E is like this, so it gets extended to E hat like this, and this function gets extended to phi hat here. Okay. Now what happens to phi hat composite E hat? That will be an extension of E inside Ex itself. Okay. But the universal property of Ex bar says that there cannot be two different extensions. Identity function from Ex bar to Ex bar is already an extension of E, right? Obviously, E composite identity is E, right? So there will be two of them, namely phi hat composite come back by E hat, and the identity. So there cannot be two. That means that this composite, this is identity of Ex bar. Exactly same way, E hat composite phi hat will be identity of Wx. What is the meaning of this? That these are homeomorphisms. Not only that they are homeomorphisms, they are commuting with these embeddings. The embedded object X goes to the embedded object. The homeomorphism, if you think of this as subset of both of them, the homeomorphism can be thought of as identity on the subset. Okay. So it is in this strong sense that we say that the Stone-Check compactification and the Wallman compactification are the same for a Tikhonov space such that its Wallman compactification is Hausdorff. We have to assume that. Okay, that is the conclusion. The general question is, when is Wallman compactification is Hausdorff? Suppose you assume it is Tikhonov space. Suppose you grant that one. Will you immediately say that X is Wx is Hausdorff? That is not a answer. You may need some more conditions. Okay, one doesn't know that. Huh? So we will stop here. This is a good point to stop this study here. We can't go on doing that. So next time we will start a new topic. Thank you.